about today, experiment number 6 is about titration. And the synonym word for titration is what? Somebody will tell me what's the name of another titration means. If I give you a quiz, what's titration? Does it mean? Titration means neutralization of an acid with a base. One of them has to be unknown, and the other one has to have a very precise concentration. So today we'll have neutralization of a vinegar with sodium hydroxide. But before this, we have to determine the concentration of our sodium hydroxide. We don't know what our sodium hydroxide concentration is. We don't know. You have to determine the exact, not the exact, the most precise sodium hydroxide concentration. In doing this, we'll use a very pure compound, standard compound. I mentioned that's how we use the standard compound. What's the characteristics of a compound that can be used as standard or as a reference compound? First of all, it has to be coming in a pure state, cheap, and not poisonous. So, and that's most of the time we use H2O, but in this case we'll use potassium phthalate, KHP, abbreviated to KHP. Potassium phthalate is a solid crystal, so you can see it there. I'll mention this one when I conclude. I'll show you. I'll conclude the presentation. I'll show you how to do the calibration, the titration itself. So titration means standardization, means double displacement reaction, correct? And means neutralization. So all those reactions meaning the same thing. You have an acid will be standardized with a base. So first of all, before we start, our goal is to get vinegar, acetic acid concentration. But we have to know first what the sodium hydroxide concentration is. So we use a very good, clean compound, cheap, and not toxic. 3 characteristics called potassium phthalate, KHP. We titrated against sodium hydroxide. And we'll be using our indicator here, which is our phenolphthalein. The unique thing about phenolphthalein in acidic medium, let me show you here, I'll come back to this setup. Phenolphthalein is an indicator, organic compound, that changes its color according to the medium it is in. If it's phenolphthalein acidic solution, it has to give you, this will be, colorless. So phenolphthalein solution inside acidic medium solution is colorless. Inside basic solution will be what? Pink, correct? When you titrate acid against base, you will get a very weak faint pink color. So you'll obtain, this is when you titrate the acid with the base. So acidic medium is colorless. Basic medium, basic solution or medium is pink. When you titrate the acid on base, you are expecting to get a faint, weak pink color. Correct? So let's go and look at the whole setup here. This is the setup here, as you can see here. So what we need? We need the purette. The purette is read from 0 on the top, zero here, zero here, ml, and it ends up here, correct? It's 50 ml. So your reading is between 0 and 50 ml. You cannot read any readings beyond 50. That's wrong reading. Above, so this one here called dead volume. This one in the tab here called dead volume. We don't know, it's not calibrated. The purettes are calibrated just from 0 here to 50. That's what the calibration is. Above 0, we don't know, it's dead volume. Below 50, we don't know, it's a dead volume. So in the first setup here, you need an indicator, the phenolphthalein, which is turned pink inside basic solution. Inside the burette, we'll have our sodium hydroxide, correct? Sodium hydroxide. You'll fill this one here up to 0. So, and then your reading will be downwards, correct? You read downwards, not upwards, downwards, because you are opening the stopcock into the Almar flask. So your sodium hydroxide called titrant. So this is your titrant here. Sodium hydroxide, your titrant, you know its concentration, and your unknown concentration called analyte. So you have to differentiate between two things. Analyte is the unknown concentration, and you have titrant, which is known concentration. You start titrating dropwise till you are very close to the endpoint. How we can say endpoint? Well, the endpoint will turn out to be pink, not at once. It will be flashing pink, and you have to be careful. Just add a little bit, less than 1 drop, maybe, just at the time, until you see this pink color. It stays at least for 20 or 25 seconds, so at least, or half a minute. So this pink color does not disappear. That will be a signal. That will signal your endpoint. So we have two things here. Oops, sorry. Let me take this one here out. So we have, if you look at this, we have here, we have two things here. Does not want to write. We have here and here. Well, we have two. I'll show you then. We have two endpoint and equivalent point. I can't show you here because the pen is not. Trying to get the pen working for me. So the equivalent point, EQ, and the endpoint, EN. We have equivalent point and endpoint. The difference between them, endpoint, you are using what? You are using an indicator. Equivalent point, you don't have to use a indicator. You don't have to use a color change. The endpoint comes after the equivalent point. First, you can see equivalent point is number of moles of the acid equal number of moles of what? Of the base. When they are equal, then you speak about equivalence point, which comes before. The endpoint, you add 1 drop more, then you can see a color change. The solution changes color. So it means the medium changes, so you can see the endpoint. So endpoint, number of moles are not equal. But equivalent point, number of moles are equal. So let's get now to the what we have to do here. First of all, we do the we standardized our sodium hydroxide. We have our sodium hydroxide back there, but we don't know the concentration of it. So how we do the standardization? Well, first you have to weigh, and this is here. I can take this one here, just hold on, make it, so you can see it here. What you have to do? First, you clean up your burette, and you set up your git stand and the burette holder as they are, and then you need Elmeyer flask, correct? And you fill the burette with up to 0 level with sodium hydroxide. So sodium hydroxide where? Sodium hydroxide inside the burette. Sodium hydroxide inside the burette, correct? Then you have to weigh. That's the first titration. We'll do 2 titrations. 2 titrations. Each titration will repeat it 2 trials. So 2 titration. One against sodium hydroxide against KHB, this one here, and one sodium hydroxide against vinegar. So 2 titrations. Each titration will do 2 what? 2 trials. So you will weigh here. You rinse first your burette, correct? Let me just get here. So first clean up your burette, correct? With deionized. Then you rinse it with a little bit of small sodium hydroxide, correct? So you rinse it to make sure the inner wall, that's called conditioning of the burette. You clean it with first with distilled H2O, and then you rinse it with H2O just a little bit. I will show you how does it works when we are done. So then you fill sodium hydroxide to the 0. Your sodium hydroxide will be filled inside what? Inside the burette. Then what you will do here, you will weigh with the weighing boat. You will weigh between about 0.3 grams KHB, potassium, hydrogen phthalate, potassium hydrogen phthalate. You'll weigh it, just a solid. You put the solid inside the Elmeyer, as I will show you when we are done with this. Then you will add 25 mL to dissolve this your KHB. Make sure everything is dissolved. You'll add 2 to 3 drops of phenolphthalein, correct? You titrate KHB until your sodium hydroxide becomes faint pink. And I showed you the color, where the color is, correct? And then when that's the case, you come in and then you go for, here it is. That's your color you are looking for. This is the color here. This is the faint, all the way up. The right corner, that's your faint pink color. So when you are done with this, you come here and you record in your data here, we have 2 titrations. We have this titration here. We have 2 titrations. First of all, we standardize our sodium hydroxide. Second, we titrate with our known concentration, our vinegar. So 2 titrations. And then we'll do each titration 2 trials. Each titration, how many? 2 trials. So the initial burette, you started with 0. And whatever is, you end up with the volume. You write the volume, then how much is the volume used. This is the initial. This is the final. This is the amount of the mass of KHB, correct? And this is the volume, correct? Initial reading and the final reading. Initial and final reading. The difference between initial and final will be your sodium hydroxide used. Then you calculate your molarity of your sodium hydroxide. So now the question is how to calculate the molarity of your sodium hydroxide here. Well, we have to go out and then up a little bit, and I'll show you here how to calculate your molarity of your sodium hydroxide. Here it is. Okay, guys. The molarity of your sodium hydroxide is given to you on the top. Here it is. That's an example of it. This is another one. Here it is. So first of all, you know the grams, suppose you put 0.3 grams of your potassium hydroxide. So the molar mass of it, you know, correct? 204. This is the molar mass here, guys. So this is the molar mass of KHP. Moles of acid, because the reaction is 1-to-1 ratio, 1-to-1 ratio here. 1-to-1 ratio, mole to 1 mole of KHP to 1 mole of your sodium hydroxide. So you divide it by its mass over the molar mass equal the number of moles, and what's here is the volume. The volume here is read from the burette. When you reach the end point, you record the volume here, correct? So you can calculate here, guys, the molarity of your what? Mass over molar mass, moles, and you divide it by the endpoint volume. You multiply you get the molarity of your sodium hydroxide. Because you are doing 2 trials, you have two concentration of sodium hydroxide. You take the average. So you take the average of the 2. And then you come here. So the mass of KHP, the solid, divided by its molar mass. And this is number of moles of KHP, which is equal number of moles of sodium hydroxide. You read the burettes. Where is your endpoints reach? That will be your volume. Transfer the milliliters into liters, and then you get the molarity of your sodium hydroxide. And you have to do it twice. 2 trials. So here it is. You have to do trial 1 and trial 2 for first with the hydrogen potassium phthalate. So you come here, you get the molarity here 1 and 2, divided by 2 to take the average. The average is here. You put the average of the 2 molarities of sodium hydroxide here. The standard deviation, you might be not knowing what standard deviation is. The standard deviation is how far you are from the average. The average in the middle. So you might be close to the average. If your data is good, you are very close to the average. If your data is bad, that's the average here. Your data will be far off. So your data is not good. So that's the standard deviation. So you have to calculate this one as well. I put for you the formula because I did not see the formula inside and I gave you an example, and this is the formula here. This is the average here, guys. See? This is the average. This is the value number. You have 2 trials. This is the value of sodium hydroxide, correct? The volume, the molarity of sodium hydroxide, the first trial, minus the average square plus the second trial, molarity of sodium hydroxide minus the average square. You take the absolute value, correct? And then you add the sum, you divide it by, you have n is 2 trials, 2 minus 1, 2 minus 1, 2 trials. And take the square root and you get the standard deviation. The lower value of Sx here, the lower value of standard deviation, the best your data. You did very well. The higher value of standard deviation means your data is far off from the average, and therefore your results are not that good. Are you following me here? So you can judge your work with the standard deviation. If the standard deviation came up to be very high, your data is not good. If it's too low, your data is good. And I give you here an example how to do this calculation. So second, after we have to determine this, look, we have to determine the standard deviation, the average. So you will be using this average here for titration of the vinegar now, correct? You will titrate certain amount of your soda or vinegar. Here it is the vinegar. See, that's the standardization, and this is the vinegar here. So first of all, before you do the calculation, any calculation, you have to make some dilution. So you have to have the volumetric flask. They are here. This is a volumetric flask, and you have to take 100 ml. This is 200. That's too big. You might look at your place. You have to have 100. Those are 200, I think. You need 100. So I think the small ones are 100. So you'll have a flask here. You will pipette with the pipette there. 10 ml. So here it is. 10 ml of your vinegar. The vinegar in the back. There's vinegar in the back. You take a small tiny beaker, fill it a little bit, and then you can pipette 10 ml of vinegar. You put it inside this 100 ml of flask, and then you will fill the flask up to 100. So then you input the dilution law, the molarity of the concentrated or undiluted acetic acid. That's you don't know. This one you don't know. This comes from the jar, from back there. You took 10 ml out of it. This is 10. Okay. This one here, you will use it to titrate the whole thing with sodium hydroxide. This one is your 100 ml. Correct? This one is your 100 ml. So the idea is to get your diluted acetic acid concentration. So you will have this flask, and then from this flask here, you will pipette what? How much? You will pipette 10 ml. So 10 ml from the concentrated from the jar, you fill it up to 100, you dilute it up to 100, and then you take out of it another 10, correct? So you take 10 out of it in the flask here, and then you add 2 drops phenolphthalein, and then you fill your sodium hydroxide up to 0 if you want to, up to 0 again, sodium hydroxide, and you titrate vinegar until you get the faint color. And then you do your, you repeat this for second titration, second trial. And now here you have to calculate your concentrated from the jar acetic acid. So you took out of this the unknown, correct? That's the concentrated, took 10 ml, correct? And the diluted is here. This is the diluted one. You took out of it 10 ml. That's the 10 ml here. 10 ml. 10 ml here. This is sodium hydroxide endpoint. This is the endpoint here. This is endpoint. Oops, sorry here. This is the endpoint. This is the concentration of your sodium hydroxide, which came out to be from the previous titration. So this one here is coming from previous titration. So this one here, MC here, is coming from this titration here, from the KHB titration. So then you can calculate your concentration of your diluted one. You could go back and then calculated your undiluted or concentrated acetic acid. We are looking at this. So this is 10. This is unknown. This is after titration of sodium hydroxide, correct? And this is how much you have taken of this diluted one, which is 10 ml. So 10 ml, so there will be the same thing. So let me now show you the same thing here. Initial final reading, you get sodium hydroxide, you get the molarity of the diluted one, correct? You take the average of the two readings, standard deviation, and then the molarity of the undiluted vinegar. The undiluted one, you have to go back and do your calculation here. You have to go back and do the calculation is in this dilution. So we have two titration. One, we have to standardize our sodium hydroxide with hydrogen KH, potassium hydrogen phthalate, The second one, we have to titrate vinegar. First of all, we have to know sodium hydroxide concentration with the help of the KHB titration. We know the sodium hydroxide, we can titrate vinegar and determine its molarity. Let me show you, I will stop the recording here. I'll show you how you do the setup here.